what we have to do? Subtract that 27. Alright.
Hey, Jalen. Here, do something. Thank you.
You want the after party? I'm alright. When is it, May? Or April? If I have my card, I know. If I have my card, I know it's my card in April, but she never said like. Hey, Miss B.
Yeah. Say again. Which paper?
Paper towel.
Yeah, you can get one if you need to. Jamarcus, you don't have yours with you, right? Alright. So yes, Naya, go ahead and get that up so we can get started. And Jalen, make sure you get your phone put up as well. Alright, let's get started.
It's never been in.
Alrighty then. So let's look at this one. I think we're starting to get better, and we're getting very similar answers. What's the most common answer I see up here? No solution. So let's actually talk through this one. So 3 times b minus 2 plus 2b equals, what was that, negative 9?
Yes, sir.
Plus 5b plus 3. Be careful, because I just realized this, I saw this on a few people where we had a positive 9 and not a negative 9. That would definitely affect our ability to answer this question, or to get this answer right. Now, I will remind you, if you miswrite something, you put a 9 there instead of a negative 9, on a test, on an understanding check, can you still score pretty well? All you did was miss a negative. You would get a wildly different answer than what you're supposed to, but remember, I'm looking for evidence of understanding. I'm looking for, do you know how to solve an equation? Do you know what it means to solve and to use our inverses, things like that? So you missing a negative and that heavily affecting your final answer does not affect your knowledge and understanding of what's going on, right? So that would just be a small, minor procedural error, and that would fall under a 3P plus unless you're also missing details. I bring this up because I want you to remember, like, I want to see what you understand. Now, there is something that a lot of us are missing. So let's look at this. First step, what did the majority of us do here? Okay, distribute. Now be careful, right? I think group 2, I talked with y'all, what did y'all forget when you distributed? Okay, some of us did in this group. I know for sure at least 2 of us did. So, it's okay, we want to learn from this and remember this. Now, I will remind you and point out, because again, some people are not sure about distributing it to both, but what is happening between the 3 and the parentheses? They're being what? Multiplied. David, why is it important that we remember there's multiplication there? Say it again. Well, we could do the inverse, right? Be careful, the opposite is only the opposite sign, right? The opposite of negative 5 is positive 5, right? So we want to be careful of that language. But it's not just that. Go back to the fundamentals. Marshall, can you help us out remembering why it's important to remember that it's multiplication?
Because it's repeated addition.
The fundamentals is that, right? That multiplication is repeated addition. So how many b's do I have being added? 3 of them, right? So what do I get? 3b. How many negative 2's do I have being added? 3 of them. So I get negative 6. Right? That's the idea of distribution. It's not just, hey, I just multiply these things. At the end of the day, we always want to remember multiplication is repeated addition. That's the idea, especially when simplifying expressions, right? And I will point out, I want to point out, we're trying to solve this equation, sure, but what is this first step that we're doing here? Remember, there's 2 different things we can really do to solve an equation. What is this first step we're doing? Starts with an S. We're simplifying. Remember, making things simpler Making them easier to work with is always a good idea. So simplify to make your job easier. Okay, Jamarcus, is there anything else I can simplify? Nothing else? Okay, does anybody see anything we could simplify then? Miracle?
The 3 and the 2B,
The 3b and the 2b?
add them together.
So remember, those are like terms, right? Literally, what does this 3b mean? I'm adding b how many times? 3. And then Jamarcus, how many more b's am I adding?
2.
So how many b's do I have on the left-hand side?
5.
5 of them, right? I'm adding 5 b's there. Then I have minus 6 equals, right-hand side,
Negative 9.
negative 9 plus 3, right? Those are like terms that we can add. So what do I get?
-6.
Negative 6. Okay, I'm going to point this out. You don't have to do this next step, but this might be something to notice. I can use what's called a commutative property to switch those. Does anyone notice anything there? They're the same. A whole lot of us said no solution here, but what is a solution? What is a solution? What is a solution? What is that? It's what makes the equation true. You just said those things are equal, right? So that's true. Is that going to be sometimes true, or always true, or never true?
Always.
Always true. This is the case where we say that there are infinitely many solutions, because it's always true. A lot of us were thinking, okay, things are going to be eliminated, but notice, and I saw some of us subtracting 5b. Remember, I like y'all showing your work on the vertical surfaces and on the desk, that's the word for it, because I can see these things. And sometimes we make small mistakes. We want to pay attention to this. 5b minus 5b is 0. 5b minus 5b, right? I'm trying to make those zeros. And 0 minus 6 is negative 6. Tell me, does negative 6 equal negative 6?
Yes.
Yes. Right? Now, over here, there was an error that was made at some point. I don't know where it was. But we get 0 equals 18. Does 0 equal 18? No. That's when it's no solution. Right? When that is a false statement. I want what makes the equation true. So if you get 0 equals 18, you made a small error somewhere. Oh, and I see where it is. We've got the negative, right? That would be still strong evidence of understanding if we then put no solution. We just missed a negative. That's okay. Alright, but we do want to recognize that would be no solution. We want to recognize over here, but this thing is always true, right? So how many solutions are there? Infinitely many. Specifically, any real number. Infinitely many solutions. I say any real number, it might be any number, period. I'll have to think about that. But what are your questions up to this point about solving, about simplifying, using our inverses, or about why this one is infinitely many solutions instead of no solutions? Going once? Going twice? Remember guys, I cannot read your minds. I'm trying to help you grow and learn. If you have a question, this is the time to ask. Okay. By the way, you want to keep out your pre-assessment because we're going to go over it today. This is going to be our direct instruction and notes on the fundamentals of solving an equation. And so I'm building it, or I built that off of the issues we ran into. All right, quick notes. Or a couple of quick notes on the agenda. First off, there's no tutoring this afternoon. I have to go pick up my son. That's not supposed to be first. I have to go pick up my son from daycare, so I cannot stay after school today. I will be here Wednesday afternoon, and I'll try to be here Thursday afternoon. I just got to coordinate that with my wife. I got to say this. I'm tired of the bathroom breaks in the middle of class. I hold it. Maybe if there's like an extreme emergency or something happens, you can talk with me, but it's entirely too many of us going to the bathroom in the middle of class. I hold it almost every day. At some point, you have to go use the restroom. Hold it, guys. Like, you're here to learn for 90 minutes. If you need to, at the beginning of class, knock out your bell ringer, go use the restroom, and that's fine. Okay, but going to the restroom entirely too much, which means we're missing learning and we need to be in here to learn. We're going to do our last famous black mathematician for Black History Month. And then we're going to do notes from the pre-assessment for solving equations. Hear me clearly on this. We are going to go over the pre-assessment so that you have direct notes that you can refer back to help you solve equations. If you're saying, hey, I don't know what to do, the notes on your pre-assessment should be your instructions on how to solve equations before we start solving quadratic equations. So take good notes. By the way, I forgot to introduce Mr. Kilpatrick is the intern from UA that will also be joining us along with Ms. Bauer. Mr. Kilpatrick, can you pass out those pink boxes? I meant to put one on each group. This is so that, sure, you can take notes in pencil if you want, but if you want to take notes in a colored pencil or a marker so that you can see what you originally did versus your extra notes, I think that would be productive, okay? And then Ms. Bauer, if there's any left, that blue one I think is there as well. And if you need colored pencils, there needs to be more colored pencils or something in the boxes, let me know because I have those in the back and I'll ask them to pass them out. After all that, writing equations for quadratic functions, right? So, quick recap from activity 4.3, then we're going to get to the extra practice that we started last week. What are your questions about what we're going through today? Trayana, you good? You sure? You look so sad.
I'm not saying.
It's a good day to learn something. Come on with it. All right. So, before we get to the pre-assessment, I called an audible literally this morning because I was looking at, reminding myself of the famous black mathematician. I was like, I feel like I can find someone more mathematically focused and someone that's more pertinent to us, and so I did. So we're going to go over one mathematician every week. Today is our last black mathematician because it's the last Monday of February. And so we're celebrating the amazing contributions of black men and women in the fields of mathematics. So we started with Benjamin Banneker, then we looked at Katherine Johnson and Fern Hunt. We were going to look at Mark Dean, but I've updated it to somebody else and I forgot to fix it here. But please don't forget, there was a theme for me. What was the theme for each one of these black mathematicians?
Astronomy, something like that.
Say again?
Astronomy or something like that.
Not just astronomy, but the first one, you're 100% right, and I think even the second one was very heavily based in the idea of astronomy. But it wasn't just astronomy, it was the study of what? The world. Science, right? Math is not random. Math is not, I mean, we've already talked about it heavily. Math is the study of what? Patterns and relationships. And where do we see patterns and relationships show up day after day after day that people, maybe not necessarily us every single day, but people study every single day? In science, in the natural world, in chemistry, in biology, in physics, in astronomy. There are patterns and relationships all around us, and mathematics is a language for that, right? These people did not just randomly start studying math because for kicks and giggles. They, most of the time, were inspired by the world around them. The example that I always go back to in general is everyone in the world's ever heard of Isaac Newton, right? Mm-hmm. Yes, the dude was a famous mathematician, but he was also a physicist, right? He developed some of the most fundamental laws that we know, but he also discovered calculus rules to help him explain those physics. Math is not random, okay? So here we are with, and I am probably going to butcher his name, but Abdul-Alim Shabazz. He was born as Lonnie Cross in Bessemer, Alabama, right? So just a few miles down the road from us. In 1949, he earned a Bachelor of Arts in Chemistry and Mathematics. Was he just a giant nerd that studied math for funsies?
Yes.
Was he a giant nerd? Yes. Was he just a giant nerd who studied math for funsies? No, he also was studying what? Chemistry. They're very heavily connected in a lot of ways. A lot of the stuff that we study in chemistry can be explained with mathematical origins or have mathematical language involved. Anytime you're talking about pH scales, right? For acids and bases, they're based on a logarithm scale that we will actually talk about within this course, right? It's not random. But he did that at Lincoln University 2 years later, earned a Master of Science in Mathematics at MIT, Massachusetts Institute of Technology, really big deal. I want to point out once again, and this is one of the things, like, I have talked about this before, he went on to a Doctor of Philosophy in Mathematical Analysis from Cornell University, so he decided to go deep into mathematics. And that's a lot like me. My origins are engineering, right? Applied mathematics, or the marriage of math and science together. But then I chose to pursue mathematics because there was so much beauty there that's what I wanted to teach. But one of the big things for me is he was born in Bessemer, Alabama. Is that a very wealthy place in general?
No.
No. So more than likely, was he born with a lot of money? Was he born into a family that had a lot? No. And he was born in the 1930s, I think. Yeah, if he, maybe 1920s actually, now that I'm looking at it. But he was born early 1900s in Bessemer, Alabama, so it was even more poor then. And education made a difference in his life. The study of patterns and relationships, the choice to engage in the world around him and to become curious about the world around him made a huge, huge difference. Went on to be an assistant professor at Tuskegee Institute, moved on to Atlanta eventually, and at the end of all this, right, in 2001, so 10 years before he died, the Association of African American Educators awarded him a Lifetime Achievement Award for outstanding work with African Americans in mathematics. Guys, your education can make a huge difference. I'm here to help you be successful, but you're going to have to pursue it and get out of your own way. I greet you every morning and I ask you to respond with what? I'm capable. Because you are capable of amazing things. Stop giving up on yourself. Stop telling yourself it's too much. Let's do what we got to do, because amazing things can happen when you chase after what you're capable of, when you start to pursue excellence. Okay. So, Shabazz is our last black mathematician, at least for the month of February. I'm considering just incorporating famous mathematicians once every couple weeks, because I think that it's fun to look at them, but we'll see where that goes. So, is that it? Yeah, happy Black History Month. It's almost over, unfortunately, but we can celebrate a little bit longer. So, what? Why is that fun?
The way you said it.
Okay. All right. So let's look here. Pre-assessment time. There are some fundamentals that we're going to be talking about. You need to take notes on these things to more clearly understand this. Math is the study of patterns and relationships. But because there's a pattern there, because there's a relationship there, we developed a language around it. If we do not become familiar with the language and we don't know the language, it's really, really hard to learn the mathematics. And I need to emphasize that more and more. Guys, if you do not study the language and understand the language, things become really difficult. So, first things first, properties of equality and distributive property. Most common mistake in step one, I see people say here multiplication property of equality. First off, at the fundamentals though, when I say a property of equality, what do I mean? Do we know? But what is that? No idea. Right here. This is a subtraction property of equality. What do you think I mean by that? That's it, right? What you've always said of what I do to one side of the equation, I have to do to the other, that's a property of equality. Did we multiply by the same thing on both sides of that equation? So is that a property of equality? Nope. So first things first, if I were you, property, yeah, we're going to do that in a second. I would make a note though of to myself that a property of equality, right? What is applied, and that's the idea of what you always said of what is done. So what is applied to one side of the equation must be done to the other side. So we're not done to do something. We're going to talk about what that something is. Sorry for anyone who might be cold. I am actually very warm, so I'm turning it down a couple of degrees. Yes, ma'am? Yes. Sorry. Where did I put yours? I have it somewhere. I might have to give you a blank copy for now. There's a blank copy until I find it later. Alright. What is the purpose of that though? Why whatever I do to one side do I have to do it to the other?
To keep them equal.
Say again?
To keep them equal. Or equivalent.
Say that one right there. To keep them what?
Equivalent.
Equivalent, right? What do we mean by equivalent? The same. Even though what?
They look
They look
different.
different. What we really mean is like there's an underlying structure about them that's exactly the same. I'm not going to ask you to know that level of language. But what we mean is even though they look different from each other, they mean the same thing. Right? So what is applied to one side of the equation must be done to the other side to make the equations equivalent. What is applied to one side of the equation must be done to the other side to make those equations equivalent. Now that's only one thing we can do to make equations equivalent. What do we start with up here to make, because I will point out, like, this top equation and this equation, do they look the same? Very similar, right? But not the same. What did we do to create equivalent equation to make my job easier to solve? By using what property? We distributed first, right? That's a way to create equivalent equations to make my job easier. What did we do to go from the second equation to the third equation? We simplified by how? What were we doing there to create equivalent equations? We added and subtracted the like terms, right? We added and subtracted like terms to, again, make the equations simpler. We want equivalent equations. By the time we get here, does that equation look at all like this equation? Are they telling us the same story though? Both equations are that every value makes the equation true. Yes, ma'am? I do not, sorry. I would just scratch it out, sorry. Alright. What are your questions about properties of equality before we make sure we have the correct answers here? I'll turn the air up in just a second. It got a little bit colder way quicker than I thought it would. But properties of equality, these are critical to understanding that I'm trying to create a new equation, right? I'm not moving stuff across the equal sign. I'm trying to create a new equation after creating zeros and ones. But if I change one side of the equation, I have to change the other side by the same amount so that my equations are equivalent. It's critical to understanding this math. Okay, so step one though, what property do we actually use? E, which was? Distributive property. Notice, and I will point this out, there was only one step here. Notice the second line every time was just simplified. So I showed, man, that was almost really bad. I can only imagine getting brown marker on my white shirt this early in the morning. All right, I showed the distribution. Most of the time, do you ever see the 5 times the 3x? No, we just showed the second step. So I showed the distribution of 5, and then I simplified. But yeah, we're just looking at distributive property. Step 2, look at that again. What are we actually doing there? What's being done to both sides? Subtracting. So which property of equality are we using? Subtraction property of equality. Like once you know the property of equality, just look at what operation we're doing. We're subtracting on both sides. So it's a subtraction property of equality. And then finally, step 3. You said D. Are we dividing both sides of the equation by the same amount? Say again.
I said yes, but I could do it.
Gotcha. I'll point this out. What's easier to say? A property of equality or what I do to one side of the equation I have to do to the other? Property of equality. Guys, the mathematical language is actually to help us make things easier once we understand the language. There's a pattern. Whatever I do to one side of the equation, I got to do to the other, or I just say it's a property of equality. That language of property of equality is literally saying the same thing. Questions, comments, concerns? Quick thumbs up if we're ready to move on. See, a handful is still writing, some of it's just too cool to put a thumbs up. Thank you, thank you, thank you. Okay. Tevin, you ready? Or are you still writing? Okay. Tyson, you good? Okay. Alright, so I skipped number 4. We're going to address things like number 4 throughout, and there's a better question later. So just make a note to yourself, skipped number 4, and I think it's like number 9 or something like that, or 10 that we'll look at instead. Okay, this one we've actually talked very heavily about. We may not have known how to do this originally, and I'm not asking you to solve this equation. I'm asking you which of the following are solutions. What do I mean by that, Trayon? What do I mean by solution? Say again. The answer to the problem? I think it's a little bit more than just that. Something about true. What? Give me some more details. Okay. Think about it for this problem though. Is it going to make an equation true? Makes the inequality true. And remember, is there only one solution? Sometimes, but like with this, how many solutions were there? Infinitely many, right? It doesn't have to be just one solution. What I need to think when I see the word solution is what makes the equation or inequality true. Or I should say what values make the equation / inequality true. That's it. I believe if you check them all, A was the only one that makes the inequality true. I believe. Nope, that's not true. E did as well. Okay. Now, I will remind you, what's your question, Jalen? Great question. So I'm going to actually go over this in just a second. So one of the things I want to talk about is how can we use the calculator to check this, right? I don't care if you know how to do this in your head. What I care is, do you understand what a solution is? Do you understand that I'm trying to figure out what makes the inequality true, right? So, first off, when I look at this point right here, what could -2 be substituted in for, Hayden? What could this -2 be substituted in for? Look at that inequality. There's only 2 variables. X. Anybody want to add on to or push back on that? Can anyone tell me why we think X then? It's an X value, right? Literally we're saying X equals -3. Remember, you can substitute things in that are equal to each other. Okay, so if -2 is being substituted in for X, Grace, what's -13 being substituted in for? Okay. So -13 is greater than 3 times -2 minus 9. I want to know if that is true. So pick up your calculator and I want you to look at that calculator. the inequality symbol is not there right away, but what symbol is an inequality symbol connected to very heavily? The equal sign, right? Notice there's options above that equal sign. So we're going to hit Control and then equals to get to the inequality. And we want the greater than, right? So I would click on the greater than symbol, and then to the left of it, I'm going to type in negative 13. To the right, I'm going to type in that expression. It's true. So I got one person saying it's true. Yes, true. It's true. Okay. Notice we're learning how to use technology to make our job easier. It's important that we understand what a solution is. Yeah, I want you to know how to simplify expressions, but we can make calculation mistakes. Now, the other beautiful thing about this calculator is, let's say I want to test multiple values, right? Instead of having to type this out every time, what could I do? Well, maybe, but click the up arrow until that inequality is highlighted. And then hit enter. And it's going to automatically bring it down. Let's test out 1, negative 6. So put in a negative 6 right for y, 1 in for x. Be careful, make sure you substitute the right thing in for x and y. So remember, be careful, you put a negative instead of minus. Hit enter. Enter. Bring it down. You put a negative instead of minus. But you still have the times symbol in there. Hit enter. You gotta get rid of the times. So delete. You want minus, but get rid of that negative as well. You see how that's slightly different? There you go. Hit enter now. All right. Okay, so when we substitute the 1 and negative 6 in, what does it say? Did you substitute 1 in for x and negative 6 in for y? Yeah, be careful. We got to be careful with that. All right, try 0, 0. Control equals greater than. No. Okay, so type in the first value, negative 13, then the greater than. So you might need to type in the number before you type in your greater than symbol. I was not aware of that. If that's giving you trouble, that's why. All right, come up, hit enter, bring it down, okay? Say again? Oh, yes, sir. Look right here. In this, the mistake you've been making since the beginning, you see where it has the multiplication symbol? So you hit the negative instead of the minus. Negative minus. Make sense? So that was what was causing that issue. Hey guys, be careful about putting a negative versus a minus in. The negative symbol is the black button next to the decimal. The minus is the white button next to the plus. Okay? You have to be careful about a negative versus a minus. All right. So that's just testing out those three. Do we have any questions about these concepts before we move on? So A and E are the only solutions here. So now we have this equation. Does anyone know what we would call this type of equation? It is one you have studied. Starts with a Q. Why would it be well, it's not a quadratic function. Remember, functions have to have inputs and outputs, right? Each input maps to one and only one output. Notice there's only one variable, but it is a quadratic equation. Tevin, why would we call this a quadratic equation? can have division without it being quadratic. Let's keep looking at it. There's a key detail here. Naisha?
The exponent got a number.
Not just the exponent has a number, the exponent is a 2, so it's second degree, right? Don't forget, if it's second degree, meaning there's an exponent of 2 is the highest power, that's quadratic, right? ax squared plus bx plus c. Second degree means it's quadratic. So what's one thing we could do to find the solution here? If we're given answer choices like this. Should we substitute numbers in still? 100%. But I want to look at this one for a different detail. This is a detail that's going to show up, right, within the rest of the unit that we're studying. The first, what was that?
It's just like.
It's right above you on that little thing. The flag.
It's a giant mosquito.
I'm saying.
Let me know if it comes back down so I can kill it. I'm too short for that. All right.
You want me to?
If someone's, you want to eat it, Jamarcus?
I ain't say that.
There's the woman. Or the yardstick.
True.
Not sure do I heard it all.
Too short for the yardstick.
I'm bound to be the first one.
It's dead.
I'm not going
It's all he says.
I don't play with
It's
this.
dead.
I'm bad at that.
A little dramatic. There you go.
The way he did it, he like flipped.
Yeah. Jacoby was good. Shania was out.
No,
All
I
right.
thought it was still alive.
It actually beat me.
You tried to.
It's a mosquito. It's not a bee. All right. So let's talk about solving this equation. I want to solve for b in this case. So what do I need to do? So I can substitute it when given answer choices, right? But let's say I wasn't given answer choices. Are there any like terms I could add or subtract? So what can I do with that negative 20? Well, not just add it to the other side. I'm going to add 20 to create a 0. And then what is it called that I have to do it to the other side? Property of equality. Remember, that's the inverse. The inverse is creating the 0. What I do to one side of the equation, I have to do to the other. That's the property of equality. So that's why I was emphasizing I'm not adding 20 to the other side. I'm actually adding 20 here to create a 0. But my property of equality dictates I do it to the other side as well. Okay, so b squared divided by 4 is equal to, say it louder, Jacoby, 25. Now we're going to talk about what's the best order to apply my inverses in a second, but we're just doing this because I want to talk about one other detail. Last detail with this, or next detail with this, I should say. Marshall, what are we going to do next? Divide 4 on both sides. Quick show of thumbs up if we agree. Nope. No way. Anybody want to push back?
Oh, no, go with the exponent.
Maybe some of the exponents. Say it again.
Multiply by 1/4.
So let's look at multiplying by 1/4. Is that going to create a 1?
Yeah, oh, we'll create a 0.
Well, what's 4 times 4? 16. Notice those 4s are in the denominator. So here's again one of the confusion parts that I want you to think about. What does that symbol actually mean? Divided by. So I'm dividing by 4. So what are we going to do again? Huh? Guys, what's the inverse of division? Multiply by 4. Right? That symbol means what? Division. That's why I wanted y'all to constantly say not b squared over 4, but b squared divided by 4, because when you say that division by 4, I want the inverse of that, which would be multiplication. Notice, what is 4 divided by 4? 0. Remember, we want to create 0 when doing what operations? Not just inverse. Adding and subtracting, we want to create a 0. When we're multiplying and dividing, we want to create a 1. Anything divided by itself is 1. Anything subtracted from itself is 0. It's important that we recognize what we're trying to create when. Okay, so multiply by 4, and so I am left with b squared equals 100. I'm going to talk about 2 important details here. What we want, hold on to that thought for a second, what we want is what makes that equation what? True. Before we even try to do any operations, I want you to think about it. What squared would equal 100? What does it mean to square something, guys? 10 times 10 is 100, right? Would anything else up here create a 100? Sure about that? What's negative 10 times negative 10? Remember, it's a negative times a negative, isn't it? So it's 100 as well. This brings up a fundamental thing that you need to be aware of. Hey, Preston, you wait. I need you focused on this because this is going to show up time and time again with this unit. So first off, Sanaya, you were thinking divide by 2, right? However, division is the inverse of what? Multiplication. We don't have multiplication here. We have repeated multiplication. What is the inverse of a square, Tevin? Do we know? Do you know what the inverse of a square is? Not sure? So I want y'all to look at these calculators because this is another thing I love about the way these calculators are set up. Do you see the x squared button on the left-hand side right below where it says trig? What's in gray right above it? A square root. Hey guys, what's the inverse of a square? A square root. There we go. So if you weren't aware of this, the whole point of a square root is that that's the inverse of a square. So what am I going to do here to get b? Square root and square root. Why did I square root both sides? Say it again. Property of equality. What do I do to one side of the equation? Got to do it to the other side to keep it balanced, right? Again, property of equality is going to show up over and over and over again. Now, I know we've talked about this before. We're always trying to create what 2 numbers when we do an inverse? Zeros and ones, yeah. Watch this. The square root of a square creates an exponent of 1. Still trying to create zeros and ones. Okay? When you take the square root of a square, and that ties into a property that we're not going to get to talk about a whole lot, but that's going to create an exponent of 1. Now, here is something you have to be aware of, and this is why I'm focusing so heavily here. You put the square root of 100 in the calculator, you know the only answer you're going to get? 10. But we just talked about it. A positive 10 makes that equation true, doesn't it? What else made the equation true? Negative 10. You have to be aware that when you take a square root and an equation, you need a positive and a negative. Because both would have made that equation true. That is going to show up again and again and again. Ma'am?
Why do you have a positive and negative?
So remember, my goal is to find out what makes this equation true, right?
Yeah.
Is 10 squared equal to 100? Is negative 10 squared equal to 100?
So you just have to have a positive and negative.
Because they both would make the equation what?
True.
True. Both a positive and negative squared would give us that. So here's the symbol, by the way. You can write out 10 and then negative 10, but there's also a symbol that tells you positive and negative. That symbol literally just tells us positive, let's say, positive or negative. That's all that means, positive or negative 10. They would both be solutions. But you definitely need to make a note to yourself here. When you take the square root in an equation, you need both a positive and negative root. Both make the original equation true. Well, I guess one of the things I would say is both squared create, ooh, I don't want to say that because of something we're going to study later. Both make the equation true. Let's say that. That's the focus. If you take a square root, the calculator is only going to give you the positive. You have to remember that there's a positive and a negative when you take that square root. And it's not just random, here's the rule, we just saw it. Both a 10 and a negative 10 made that equation true. Right, David? Tired of me talking? I feel you. I'm tired of talking to you. I'm sorry. We'll get there. Okay. But this is the first introduction into a key idea that we're studying with the unit that we are currently on. What are your questions before we continue to the next problem? Yes, ma'am.
I thought you said it was gonna be 4 times.
You thought what? Say it louder for me.
4 times.
4 times 4? This 0?
No,
I got a 1. Notice, what is the symbol? So that is 4 divided by 4. I'm multiplying here, but think about this. That'd be 4b squared. 4 times b squared is 4b squared. And it's still divided by 4. So what is 4 divided by 4? That's creating the 1. Does that clarify that for you? You can also remember that 4 is always understood to be divided by 1. So when I multiply across, I get 4b squared. 1 times 4 is 4. And then I divide. I just kind of skipped half a step there. Good question though, for clarity. Yes, Jayla? How was what? That one? Remember, we talked about it right here. When I substitute in, if I square a negative 10, what does it mean to square something? So, that's negative 10 times negative 10. It's because we're doing a negative times a negative that it will have to become what? Positive. So both 10 and negative 10 give me a positive 100. And that's why we need both a positive and a negative. Every time you take a square root, you need both a positive and a negative. Okay? Be careful. Please hear me very clearly on this. Because Jalen tested on the calculator. Jalen, did you put parentheses around the negative 10? Put parentheses around that negative 10. We talked about this before. If you put it in like this, your calculator understands the order of operations probably better than we do, and it's just doing 10 times 10 and then taking the opposite of it. You need parentheses so it becomes negative 10 times negative 10. Makes sense? That's the issue. Good question. And I'm glad you checked that. Alright, number 7 for the most part we're pretty good. I do want to point out number 8. We're going to talk about this very briefly. I want to solve for x, right? And x is on both sides of the equation, so I need to make one of them a what? Remember, I want to create those zeros and ones. We only want it on one side. Make sense, Jamarcus? It was already a 1x. But I can't do x plus 1. They're not like terms, but x minus x is 0. Minus x is? Oh no, I get 1 equals 0. Phoebe, is that a true statement? No, so what are we going to say here? No solution, right? That's not true. That can't be true. So no solution. Can't be true, so no solution. That was something that a lot of us were missing last time. But that's important to recognize. I think we got that pretty well on Friday. But I just wanted to re-emphasize that. Okay, number 9. This is the last critical detail to know about quadratics for this unit. I'm going to point this out really quickly. Does anyone recognize this as something we've actually looked at already? Not necessarily equal to 0, but... Huh? That's factored form, isn't it? There we go. Remember, if this was f of x equals x plus 1 times x minus 3, that would be our factored form. But right now, what's in the place of f of x or of y? Hey guys, what type of points are we looking for when y is 0? If y is 0, we're looking at what? X intercepts, right? X intercepts. I'm about to explain to you a little bit more why we need the opposite here. We should know what's R1 in this case, the first root. What? Yeah, x minus R1. We need the opposite, right? X minus R2. R2 is going to be a positive 3, right? So when I look here, we know from our understanding with roots that we need the opposite. But there's something else here that is actually super important to what we're going to be studying, and it is called the zero product property. First off, what's a product? What you get from multiplication, right? And guess what? If I multiply by 0, what do I always get? 0. So if I tell you that a times b equals 0, what do you know about a and b? A or b?
1 0.
At least one of them has to be 0. The only way that the product is 0 is if one of them is 0. So the zero product property, at least a or b has to be 0. Y'all, this is a critical property to a lot of what we're going to study over the next 2 to 3 units. You have got to know that zero product property. We're going to see this for 2 to 3 units at least. You better know that zero product property. So here's how it applies here. To get a product of 0, at least x plus 1 or at least x minus 3 has to equal what? 0, right? That's the application of the zero product property. At least one of those factors has to equal 0. Okay, now how would I solve that equation? This first one. How would I solve for x? Minus 1, minus 1. Create that 0. Hey, what does x equal to? Hey, you see how that's the opposite of what's inside the factored form?
I don't like this.
Say again.
I don't like this.
Why do you not like this? Because it's brand new, even though it shouldn't be. We should have learned it in Algebra 1. Guys, I need y'all to remember, when you first learn something, it's natural not to love it. We get comfortable with it over time. This is the first time we're seeing it. Okay? We're going to keep working with it. But if you understand the zero product property, at least one of those factors has to equal 0. So we set our factors equal to 0, and then we solve it like we've always done. And again, does it show that my root is the opposite of this sign right here? Yeah. It's just telling us the same story from a different perspective. What would I do to solve this equation? Add 3. Negative 3 plus 3? Add 3. X equals? Do I get the opposite again? Uh-huh. Guys, math is not random. It's not 1,000 different rules. It's telling us the same story over and over and over again if we understand it. I'm particular about mathematical language because when we understand the language, it is something that can be applied in lots of different ways instead of just learning a rule to get us to a test and then we forget the rule after the test. The zero product property is going to show up over and over and over again in mathematics. Okay, now we'll answer what questions do we have before we continue. Yeah, x equals negative 1 and x equals 3. There's my solutions. Notice those are the same as my roots for this factored form. Questions, comments, or concerns? I'm just erasing this one right here. Hey, you don't have to be that angry, just punching a wall like that? Just, hard time. Alright. Pressing you alive? Okay. So, here's where I want to briefly talk on number 10 about the best order to solve an equation. So make a note to yourself, because this is something I saw us getting tripped up on. Best order to solve an equation. Let me ask you a question. What is the order to simplify an expression? PEMDAS is the acronym we use for it, right? Parentheses, which when we say parentheses, we really mean any type of grouping. You see how all of this is grouped together? Even though there's no parentheses there, this is grouped together. Okay? Then exponents, then, and I always put them together. They're the inverse of each other. They're the same thing. You know, I can always rewrite one as the other. And addition and subtraction. Now, there's nothing I can simplify here, is there? No like terms I can add together? Can't simplify. So I'm going to use a what to start solving this equation. Starts with an I. Say it again. Inverse, right? Because we're using inverses, I'm going to invert this order of operations to simplify. The last thing that I do when simplifying is adding and subtracting. The first thing I do is any kind of grouping. You see how all of this is grouped together? That's the last thing I'm going to deal with. The first thing I'm going to deal with is addition and subtraction. So what am I going to get rid of first? That 3. So subtract 3. Create a 0 there. Boom. Now I've gotten to all the stuff being grouped together, right? So, one thing I'll point out is all of this is grouped together, but also, isn't this also grouped together? So that grouping stuff is what I'm going to deal with last. So what am I going to take care of right now? So we're dividing by 2. So remember, all of this in the numerator is also grouped. Yeah, this is all grouped overall, but this in the numerator is grouped as well. So outside of that grouping, I've got division by 2. So I'm going to multiply by 2. Now I want to pause before you write this down. I want to point this out, because this will also help you understand. Here's the x that I want to solve for. What is the very first operation applied to the x? Multiplication by 3. What's then happening to this 3x? It's what?
Oh, wait.
Look at that expression. What's happening to that 3x? It's being, no, after the 3x. Subtracted by 4. What's then happening to 3x minus 4? It's being divided by 2. What is the last thing being done? Division by 2? So that's what I'm going to take care of. The last operation being done is the operation that I'm taking care of. Division by 2 is the last thing, so I multiply by 2. Okay, so I'm going to leave that there for a second. I'm going to make a quick note here. When using inverses to undo operations, invert the order of operations to simplify. Undo the last operation of the expression. Okay, so when using your inverses to undo operations, invert the order of operations to simplify. That's PEMDAS. That's the order of operations to simplify. Which means we're going to undo the last operation in the expression. Is there any of that language that I need to clarify? If you see anything you need to ask a question about, let me know. But that means I'm going to continue this. So 3x minus 4 equals negative 30. Add 4. Notice 3 times x, then minus 4, so the last operation is what I'm undoing. 3x equals negative 34. And then you can divide by 3, but remember I recommend multiplying by 1/3. It's going to help with your exponential functions. And you can leave it like an ugly fraction. I don't care. Yes, Tyson?
Ain't going to be 26.
Thank you. 100%. Thank you for catching my error on that one. Guys, please understand mistakes happen. I ain't sweating it, I'm glad someone caught me on it. Reminds me that even I need to pay attention sometimes. Alright, what are your questions before we continue? Yes, ma'am. Now, let me clarify. You can do it in other orders, but that's going to be the simplest. Okay? So, hear me very clearly on this. My whole thing is, as long as you understand